Okay.
And these are just the same. Yeah. Yes.
So you know what the weirdest part about me doing the live office hours these days? When I rewatch it and I see the back of my head. Because I'm not used to seeing the back of my head. Well, let's get some chemistry questions. Most of you have questions about the buffers lab, yeah?
Yeah.
Buffers lab, buffers lab, buffers lab.
Quick question. When we were calculating the pH of the original buffer, like the calculated version, we found like the moles of the A- and moles of HA-, but we knew that there was like 250 milliliters, but we divided it by 5 to get to 50. Are we not supposed to do that? I'm not really sure why, but this is what
divided by 5.
Dr. Redsick helped us. Like right here.
You got your moles of A- and your moles of HA, and you divided by 5.
Because we weren't sure if that had to be 50 milliliters that we were using, or if we could use the 250 milliliters.
Oh, so it depends on which thing you were calculating at the time.
So for this one, if it's the original buffer.
And let's all scoot in a little bit more. So is this the original buffer adding things to the original buffer?
It's original buffer after 1 milliliter.
Yes. Okay, I know what's going on. So let me give you the short. Let me give you the long version of what you're doing with all of your calculations. I'll give you the short version first. You ready for the short version?
Yeah.
Stoichiometry, equilibrium. Is that a surprise? No. Okay, so let's go ahead and look at the stoichiometry and the equilibrium. I'm going to do it generically for HA since some of you have the sodium dihydrogen phosphate, some of you have the acetic acid. So first we'll look at the reaction. HA plus OH minus goes to A minus plus H2O. I'll put it on there small, but we don't really care about the H2O. Then we've got the second thing we care about. I'm going to do that here. Then we've got the equilibrium. And since we're always going to be in the buffer region, we always get to pick which equilibrium we look at. So we'll look at HA. We're going to look at H2O. Again, I'm putting H2O small in first because we don't really care about it, but it's important that it's there. H2O plus HA goes to A minus plus H3O plus. This is going to be an ice table. This is going to be a stoichiometry table. Now, what things do we do the same and what things do we do different between all of these? Essentially, the main thing to figure out for all of these is how many moles of HA are you starting with, and how many moles of A minus are you starting with? That is the essential question for all of these different parts. And then you're going to add some OH minus. You're going to add 1 mil or 4 mils or whatever. But the main thing that we're going to have to figure out, whether we're looking at the original buffer, or if we're looking at the dilute buffer, or if we're looking at a portion of the original buffer, right? Then we're going to say, okay, how much do I have in each? So when we look at the original buffer that we made, when we did our original calculation, we calculate how many moles of acid we need, and we probably need 25 millimoles there. And we start with 0 A minus there. That's what we do pretty much all of the buffer problems we've done until you get to part 2 in this lab. All the ones we've done in class have been set up like this, where you have to find your OH minus to make some conditions here at the end. Now, we're going to skip the entire ice table by using Henderson-Hasselbalch. Let's all scoot in a little bit more. Someone can take the nice chair if they want. Right? We're going to be able to skip the entire ice table by using the Henderson-Hasselbalch, recognizing X is small. So my initial HA is the same as my equilibrium HA. My equilibrium A minus is the same as my initial A minus because X is small. right? This is one of the tricks that we've used. So that way I can skip the ice table and just jump straight to Henderson-Hasselbalch. We can use another trick. Because the total volume is the same, we can get rid of this equation and we can switch it to be pH equals pKa plus log moles A minus at the excess point divided by moles HA at the excess point. Right? So if I can get these numbers at the end here, I can plug those directly in.
These are the volumes the same?
Yes, if the volume total for the A minus and the HA is the same, then concentration divided by concentration, volumes cancel out.
Are we not adding 1 milliliter of base? Is that what we're doing here?
This is the moles at excess. The OH minus is going to be a start.
Okay.
Right? And still, you're adding that 1 milliliter to a beaker. So then the A minus and the HA are still in the same volume.
Okay.
Right? So the main thing that we care about is how do I do my stoichiometry? At this point, we're now doing a 127 problem. Right? We've completely gotten rid of the 128 work by using Henderson-Hasselbalch and this kind of simplifying argument that the total volume is the same. So I just need to get my moles of A minus at the excess point. That should simplify the thinking to some degree. So we can, as soon as he knew I was recording, he left. You can watch live too. Oh, too late. Now all we have to figure out is how much of each of these things do I have? So who wants to give me their numbers for an example? Go. So first thing we did, let's start with this. First thing we did was make a buffer. We had 250 milliliters, and we had it at 0.1 molar concentration. Right? So I know that we start with our 25 millimoles here. Somebody, how much base did you add?
Wait, how do you know that it was 25 mil? Okay.
0.1 times 250?
9.6 milliliters. 6.7 milliliters of base.
We're using yours. 9.67 milliliters of base. And what concentration was that base that you added to make this? 1 molar base. This tells us that this OH minus is going to be 9.67 millimoles. In our original buffer, we start with 0 A minus. Right? That's weird. We start with 0 A minus. So now I can go ahead and do my calculation. I'm going to have minus 9.67 minus 9.67 plus 9.67. I get 0. I get 9.67. And 25 minus 9.67 is 15.33. Now, if we plug 15.33 and 9.67 into this equation here, we should get your target pH. That is to say, the pH that you were trying to make. Right? That's for making the original buffer. The real question you all want to ask about, though, is what about part 2? You all did your original buffer calculations correct. We did the lab pal for that to make sure. You checked before class to make sure. But what about part 2? Where you take a portion and then you react to that portion. We'll do part 2 in this obnoxious orange color just because I've used all the other colors already.
Part 2 is in the diluted buffer?
The diluted buffer or just adding to your buffer. Let's do the original buffer first. So you take your original buffer and you add, let's just jump straight to adding 5 mils.
So this is a number that we already should have calculated, right?
This is part number 1? Yeah, that was the pre-lab.
Okay, yeah.
But the reason I wanted to do the pre-lab was to show you that all of the calculations in the lab are actually just a slight variation on the pre-lab. So let's see how that's true. Add 5 milliliters of 0.1 molar base to, now we're going to add this to the original buffer, but we're not adding it to the total original buffer. How much of the original buffer do we take? Is it 50 milliliters? 20 milliliters? 50 milliliters?
20.
20 milliliters. We're going to take 20 milliliters of original buffer, plus how much water do we add? Does the 180 water change our moles at all? No. It just makes so we can put the pH probe in there more easily, right? This 180 milliliters of water. Remember, since everything we're doing is essentially stoichiometry, adding water doesn't change our stoichiometry. Yes?
Really quickly, going back to step 1, the pH that we calculated there, is that the measured pH of the original buffer?
That should be the measured pH of the original buffer.
Okay.
Right. Now, we have to do a couple things here, right? We are adding 5 milliliters of 0.1 molar base. I'm going to erase these numbers. I'm going to... I want to save some of these numbers. I'm going to save the 15.33 and the 9.67. I'm going to need those in just a moment, but I want to erase everything else in here so we can do part 2. So for part 2, I know I'm adding 5 milliliters of 0.1 molar base. So that's going to be 0.5 millimoles here. What number do I put for my HA? I know I had, in my buffer, I had 15.33 millimoles.
Times.
But I only take 20 mils of it. So I'm going to have, can I do this right?
306.6? 15.3 times 20.
Now, if I'm going to be doing something with volume, I actually want to put it in terms of concentration. So I'm going to divide by my 250 original, and then I'm going to multiply by 20.
Wait, why are you dividing by 2?
So I'm dividing by 250, so that's milliliters per millimole, because that was my original volume, right? You filled to the 250 mark, right? So I need to figure out how many moles of this I took. Now, I took 20 milliliters out of the 250. So if I do 15.33 times 20 divided by 250, that should tell me how many moles I took.
1.226, 1.23.
So we're multiplying it by 20?
Yeah.
I am multiplying by 20 and dividing by 250. If you've got it in concentration, you're just multiplying by 20. If you've got it in millimoles, you're dividing by your total volume and then multiplying by 20. So notice, in this situation, now I've got my start moles. Oh, I have to do the same thing over here for my A minus, right? Because I had some A minus present, 9.67 divided by, I'm just going to do this, 9.67 times 20 over 250, right? My milliliters will cancel out, and it'll give me the portion of moles that I'm taking. Right, so you can imagine if you were adding 1 milliliter of this 0.5 millimoles to your original buffer, and like all of your original buffer, you'd have 250 divided by 250, your millimoles wouldn't change. If you were adding to half your original buffer, you'd have 125 divided by 250, you'd have half the moles. If you were doing it to 25 milliliters instead of 20, that would have worked out a lot better mathematically. But if you were doing it to 25 milliliters, you would have had 1/10 of your moles, right? So this proportionality says, how many moles of my original buffer did I take? 9.67 times 20 divided by 250, 2/25.
0.77.
So hopefully that logic makes sense in terms of why I'm multiplying and dividing by volume, right? It's essentially an M1, V1, M2, V2 calculation.
So 15.33 times 20 is 250 times, okay. So you're finding that.
And this was 5 times 0.1. This number just comes from the fact that I'm adding 5 milliliters, 0.1.
Yeah.
Now, at this point, we've calculated the correct amount of starting moles. Can you do the stoichiometry? After we got our excess, we just plug back into this thing like we did last time.
We just do the acid over,
Yeah.
or the base.
So I'm going to have my hydroxide limiting, so I'm going to have minus 0.5, minus 0.5, plus 0.5. I'm going to have, I think I can do this in my head, 0.73, 0,
Yep.
and 1.27. And we can notice a couple things right away before we go to the Henderson-Hasselbalch equation. Right, so we're essentially doing the same thing we did in number 1, except for now we're doing it with different molar amounts. And we can notice something important already. It shouldn't be surprising. I added base. I have more conjugate base and less weak acid. That should make my pH go up. That's what we should see. This was for the 5 milliliters. If we were doing the 1 milliliter, we did the same thing, except for we changed to 0.5. It'd be 0.1 instead. Also notice, and you should have this in your data as well from what you collected last week, adding 5 milliliters of the 0.1 molar base, I'm still in the buffer region. I still have weak acid and conjugate base both present. I have not gone out of the buffer region.
So that number should be our calculated pH for the very diluted buffer.
No, this is for the original buffer. So this is why I could do the 20 to 250 directly. I didn't have to worry about the milliliters of water added in. I'm looking at the original buffer after adding 5 milliliters of sodium hydroxide at 0.1 molar concentration. When we do that, we can calculate the pH, and we should get a pH that's barely changed because we're still in the buffer region. So we should still be within plus or minus 1 pH of what we started with. Now, are you ready to do the dilute buffer? Are you ready?
Yeah.
So confident. Okay, here we go. I'm going to erase everything in orange. I'm going to keep these original numbers from our original buffer. That's from the whole 250 milliliters. That's going to be important. But I'm going to erase everything else. And I don't want to use that orange pen again, so I'm going to use the black pen. I'm going to label this original. I'm going to call this 2B. Dilute buffer. Now, you all should already at this point be able to tell where we're going to do and what we're going to do. That sentence didn't make sense. Where we're going to go and what we're going to do. We're starting, we essentially need to figure out how many moles we start with and how many moles we add. Let's do it for 1 milliliter this time rather than 2 milliliters.
Wait,
I think we're doing the
We are doing the dilute buffer when we add 1 milliliter base.
Oh, really?
I thought we measured.
Don't have, yeah.
you have to calculate and measure it.
We didn't have to calculate that. It just says
It just says measured.
Oh, you should totally calculate it.
Mine says calculate.
No,
ours says.
What?
Yeah.
We're in different.
Oh, you're not in my lab. Yeah, my lab has to calculate this.
No,
We're in your
Wait.
lab. They're not.
My lab.
Oh. Oh, my lab should have to calculate it too. I can't believe that got taken off.
Could you go over it?
Yeah.
Yeah. Because this is, we've got, I don't know if you remember, we do have a midterm this week.
We
This would
remember.
be a great question for the midterm. So, how do we deal with the dilute buffer? And if you're in my lab, I'm gonna send an email out that's like, do this. Because like, I gotta find somewhere that you have to do this. Maybe I'll put it on the quiz this week. I don't know. The lab quiz, lab quiz. Lab quiz, midterm, homework quiz, all of it. No, I'm kidding. So essentially, we should know where we're going and what we need to do. We need to find the moles that we're starting with, and then just do the stoichiometry. But with the dilute buffer, the thing that really trips up most of the students is they forget how they made the dilute buffer. They don't keep track of the number of moles they have. So let's keep track of the number of moles we have. How did you make the dilute buffer?
You take the original buffer and you add the water.
How much original buffer?
20.
You do 20 milliliters plus how much water? Oh, I just realized I messed up that last calculation too. Because
It's supposed to be.
no. So you take 20 and then you add 180 and then you take 50 mils out. And I forgot to take the 50 mils out. So notice, I'll fix it right now.
That's what I was asking about earlier with the 50 milliliters.
Yeah, exactly. So we take 20 mils of our original, we add 180 milliliters of water. So that means I'm going to have 15.33 divided by 250 times 20. That's going to give me my moles in dilute. Right? Which is, we did it for that originally, but you didn't do the entire 200 milliliters, right? Then you only took 50 mils of this, right?
Okay.
Yeah.
So then you're going to have to take
1.2. Except for this one or the one that we just did?
This was the previous one.
So for the previous one, oh, I totally did that dilute buffer for the previous one.
Yeah.
Okay.
That's so irritating. So what I did for the previous one, the problem in orange that we just did was actually if you took the original buffer, if you did it for all of your dilute buffer, right? If you did it for you took your 20 mils, you added 180, and you had 200 mils of buffer, and you added to that full 200 mils of buffer. That's the experience. That's what you would have gotten. Now let's do it if we only take 50 mils of that dilute buffer. I'm just going to delete this video. It's not going to exist. I'm kidding. It'll exist still. So now we want to take 50 mils of the dilute buffer. So how do we get 50 mils out of this? So what you're going to essentially do is this is going to look a little bit weird, but let's actually, so it doesn't look too weird. How many moles in your dilute buffer is that? What's that equal to? We just did that. It's like 1.2 something, right? 1.23?
3, yeah.
That's in 200 milliliters. So if I'm going to take 50 milliliters of my dilute, I'm going to have 1.23 times 50 divided by 200, right? I want that portion of the dilute buffer. So this is where most students make a mistake, and even I made a mistake. I just lost track of what I was talking about. It is you take a portion, and then you take a portion of that portion. So you have to cut it twice. Did you get all your questions answered?
Yeah,
this good?
sorry,
Okay.
I have to go.
No worries, see ya.
Thank you.
So this is how I messed up the original buffer calculation, the one we did in orange. That calculation in orange.
So how do we fix that calculation in orange?
That calculation in orange, we'll have to go back and redo that calculation in orange. I'll make a note in the video that's like, don't look at that.
Wait, so don't you just redo it by doing like this, and then you'll subtract the like limiting one, and then
Yeah.
you just, so it's not.
It's the same logic is totally fine, right? So the problem I had in the orange calculation was I was taking a portion and diluting it, and then I didn't take the second portion because originally you should have just taken 50 mils of the original buffer, which is where you get 1/5 of it, right? Because you get 50 over 250. You're taking 1/5 of your original buffer, and so you get 1/5 for your starting moles. This one, we're taking 20 mils, we're diluting, and then we're taking 50 mils of that diluted buffer. So we have to do 1.23 times, what was that, 1/4? If I can do that in my head. I can't do that in my head. Please help me calculate this. Oh, I stood up too fast.
And then this is going to be the moles of the dilute buffer that we're going to put
Mm-hmm.
up here.
0.31.
We have to do the same calculation with 9.67. So we have to do 9.67 times 20 divided by 250 times 50 divided by 200.
So the
Right.
15.33 and the 9.67, where are those ones coming from?
Those were from whoever gave me their sample data. Those were the values that we got when we originally made our buffer. Right, when we originally made our buffer in the 250 ml volumetric flask, this is how many moles of weak acid and conjugate base we had in our flask. We then say, okay, I'm going to make some dilute buffer by taking like 20 mils out of this 250, which gives me some number of moles I'm taking from my original buffer. And then I'm going to dilute it, and then I'm going to take 50 mils of that diluted, right? So I'm taking two portions. I have to do two cuts. Did you calculate the A minus?
That was your 0.19.
0.19? Okay. Now, this is where it gets interesting. Notice the amount of HA and A minus you have. When we take this double cutting of it, right? At this point, we can notice if I add more OH minus than 0.31 moles, I'm going to break my buffer. So if you look at your data, how many milliliters, or just think about it, how many milliliters of base of 1 molar, 0.1 molar base can you add before you break your buffer?
Wait, are you saying how much base can you add? Yeah, what it?
0.31 moles worth, which would be 3.1 milliliters, right? Because it's 0.1 molar. So you can add a maximum of 3.1 milliliters before you break your buffer. How many milliliters did you add the first time? 1. And you should get something where you're still in your buffer range. How many moles did you add after that? 4 more, 5 total. You should see your pH dramatically jump because you go outside, you go past the equivalence point. Did you see that in your data? This is mathematically how we explain what you saw in your data. If I had 0.1 there, this is all fine. If I have 0.5 there, the buffer breaks, right? All of a sudden my OH minus becomes the excess and my HA becomes the limiting. So you should be able to do those calculations. Notice each of these is calculating how many moles you start with and just doing the stoichiometry. After you do the stoichiometry, plug into this equation. Right? Should we fix that original buffer calculation now? It's much easier than I made it out to be. I'm not going to finish this one. I'm going to let you finish that one on your own because it's the same thing over and over again. Let's go back and fix this one in orange. I'll even do it in orange again. If I could spell. This is how we fix that one. I just got ahead of myself. I got sidetracked. I got too excited that I was on camera. Whatever. All we're doing in this one, we'll do the 5 milliliters, 0.1 molar base. 5 milliliters, 0.1 molar base. How much buffer? Again, notice what we have to keep track of is how much we start with. So how much buffer did we do in part 2 with the original? 50 milliliters, right? Not that nonsense I did before where I took like 20 and diluted and all that. We just want to do 50 milliliters. 50 milliliters of the original buffer. That means to get my moles, I'm going to do 15.33 times 50 over 250. Now that 1/5 makes sense, right? Because that's the molarity. If we do this, so it is in terms of a concentration calculation. Right? Molarity, moles over liters, times volume gives me moles. That's exactly what we're doing. And it just happens that because you are taking 50 milliliters out of your 250, 50 divided by 250 is 1/5. That's where that magic 1/5, like, oh, just take 1/5, comes from the actual what you physically did in the lab. What if you took 100 milliliters instead of 50? What if you took 10 instead of 50? You should be able to do all of those calculations based off of this idea.
Wait, is 15.33 in milliliters?
It's in millimoles. Right, so here, let me put my units on here so it doesn't get too confusing. That's millimoles, that's milliliters, that's milliliters. Right, so this becomes a concentration, millimoles over milliliters. This will give me molarity. Then I multiply by milliliters and it'll give me my millimoles again. I'm figuring out what portion I'm taking. So that's going to be like 3.07.
0.031.
What is it?
3.066.
What is it?
3.07.
3.07, 3.066. That is in millimoles. I think you've got it in moles.
Yeah.
Right? So if you're converting your milliliters to liters, right, you're going to be doing things in moles instead of millimoles. I just get tired of converting milliliters back and forth, so I like to do things in millimoles. So that 3.07 is the value we have here. We do the same thing with 9.67. I can't do that one in my head. I'm having trouble.
I got 1.934.
That sounds good. 1.934. We'll got 1.93. Close enough. Now we can look at this and say, okay, how much hydroxide do I add? And if we want it to be more interesting, we can say, how much hydroxide could I add before I break my buffer? If we're adding the 0.1 molar base, we could add 30 milliliters before we break our buffer. I'm going to add that to the future calculations. How much would you have to add to a certain portion? I got to write that. I got it on video, but I'm going to write it down. That's a good question.
So you have to have 30 because it's times 0.1.
Right, exactly. Right, so if we added 30 milliliters, it would break the buffer. We don't add that much. How much do we add? If we're adding 5 milliliters, we're adding just 0.5. And again, after we do that thinking, after we do that logic, we're now just at a stoichiometry problem, right? With a 1-to-1 mole ratio, right? It's not that hard. It takes a little bit of thinking, but it's not that hard. We're going to have minus 0.5, minus 0.5, plus 0.5. This is 0. This is 2.57. This is 2.43. Still in the buffer region because you still have weak acid and conjugate base both present. You should find that your pH doesn't really change. Not much. Whether you add 1 mil or 5 mils to your original buffer, it doesn't really change. If you added 1 mil or 5 mils to your dilute buffer, if you did it to the whole 200 milliliters, it doesn't really change. If you do it to a 50 mil portion of that dilute buffer, It does change.
So we would add this to that equation.
Yeah, and then you're going to take this, and it's going to go in there, right, to our specially modified Henderson-Hasselbalch. Now, in all of this, there's a couple things to keep in mind. Thing number one, we're really just doing a bunch of stoichiometry and skipping the equilibrium thanks to Henderson-Hasselbalch. So all we have to worry about is the number of moles that we're reacting and doing the stoichiometry correctly, which means if you've got a solid foundation from 127, this isn't that hard. If 127 is a long time ago, or if you squeaked by a little bit, this could be harder. Thing number two, everything we're doing, since it's just messing with the stoichiometry, everything we're doing is really just changing the buffer capacity, right? How much base can I add? And when you think about the three things that buffer capacity depends on, concentration of what you're adding, concentration of your original buffer, and amount of your original buffer, right? Those three things, as we vary those three things, we change how well our buffer can handle having material added to it. Question?
So just to clarify, it's like not unusual if our calculated pH for the original buffer after 1 milliliter and 5 milliliter are like very, very similar.
Hardly changed, right?
Okay.
Still in the buffer range. They should change. They should still be going up, right? They should still be going up some, but the ratio here is not dramatically different. So still should be about the same.
And
But
then
for the dilute buffer,
when we do like after the 5 milliliters, it makes it so then would we do like, or at least what I'm seeing here with my calculations is that when you do for your HA, it comes out to be 0. And so then you would just do like the 0.5 or whatever your thing is divided by 0. So it's like log of 0. And then, or.
Can you have actually a 0?
No.
So there's another question that we can answer that we haven't talked about, where we can talk about when we break the buffer, that is to say, when we go past it on the titration. I'm going to call this number 3. I know it's not a question. I guess it's kind of, let's call it 2C. So if we're looking at the lab, this is still in part 2, but it's like when you're doing this to water or you're doing it for the dilute buffer, what happens when you break a buffer? So in this case, I'm going to go back to that dilute buffer. If I can remember correctly, it was 0.31 and 0.19. Great. And then we're going to add 5 milliliters. So we're going to have 0.5. What's my limiting reactant in this case? Not sodium hydroxide. So it's the acid. So I'm going to have minus 0.31, plus 0.31. I'm going to get 0. I'm going to get 1.9. Sorry, 0.19. 0.19. And I'm going to get 0.5. Can we use the Henderson-Hasselbalch equation if we are not in the buffer region? Well, first off, are we in the buffer region? Got conjugate base?
No.
I got no weak acid. We're not in the buffer region. We can't use Henderson-Hasselbalch. So that means we can go and look at doing our equilibrium. In this case, the equilibrium has to be because I've only got A minus, my equilibrium must be A minus plus H2O. A minus plus H2O goes to HA plus, OH minus. Now, I'm gonna tell you right now, you don't need to do this ice table. But let me show you why you don't need to do this ice table. We've got 0.5 millimoles divided by total volume is going to be 50 milliliters plus 5, 55 milliliters. HA is 0. My OH minus is going to be 0.19 divided by 55. I'm going to go ahead and do my excess small approximation. What am I trying to find here?
The concentration of the acid, which isn't going to help with the pH.
Well, really, if I find my OH minus concentration, that gives me my pH. If I make the excess small approximation, what happens to my OH minus concentration during equilibrium? It stays the same. I'm still going to end up with 0.19 divided by 55. So that means as soon as I've got this number, that number is my OH minus concentration, which gives me POH, which then gives me pH. I don't need to do the ice table.
Don't you need divided by 50?
You still need the total volume, right? You still need the total volume. You still need to get to OH minus. You need to do a calculation to get that. But you don't need to do the ice table because, and this is why on every titration curve, past the equivalence point looks the same. It's just excess OH minus, right? That's why the pH doesn't change much, because as you keep adding more and more OH minus, your concentration is not going up that fast. So all you do is you say excess OH minus. That's what determines everything past the equivalence point. It's just excess OH minus. That should get us through all of the lab calculations. Should. Do me a favor, look over your labs, look over anything else you want. Take a moment, see if you got any questions.
So the buffer, oh, sorry, go ahead.
I was going to say, for some of the calculations, like, I used Beer's law, like, taking the absorbances.
Yep.
And then with the molar absorptivity, like, turn that into concentrations. And then within the buffer region, just plug that into Henderson-Hasselbalch.
So after you've got those concentrations, yeah, you can plug this directly into Henderson-Hasselbalch to determine your pH.
Yeah, okay.
So we're essentially determining pH two ways. We're determining pH from the indicator, and we're determining pH from the stoichiometry.
Okay.
And those things should match up, but we can check if they match up.
Okay, yeah, and I just realized, like, the Henderson-Hasselbalch doesn't work outside the buffer region. It's like I was getting, like, pHs way off for the ones where it was outside the buffer region.
Which totally makes sense, right? Because it doesn't work.
Okay.
So outside the buffer region is where you no longer have both the acid and its conjugate base.
Correct.
And then, like, would the buffer region be like where the pH, like pH equals pKi plus or minus 1? Is that the buffer region? Okay, I just wanted to make sure I had, like, there's a lot of conceptual stuff and it all gets out.
Yeah, so there's two ways where we can tell whether we're in the buffer region or not. One, from the stoichiometry, we can see that we don't even have any HA left. If you've got no HA left, you're not in the buffer region.
Okay.
Right? That's thing number one.
Mm-hmm.
Thing number two is calculate the pH. If you plugged in, if you like didn't recognize that you were outside the buffer region, and you tried to plug this into the Henderson-Hasselbalch equation, you would have 0.5 divided by 0. Log of 0.5 divided by 0 is the log of infinity.
Mm-hmm. That's not.
That doesn't work out,
Yeah.
right? So we should get a pretty good hunch that Henderson-Hasselbalch. Let's say, okay, 0.5 divided by, instead of infinity 0, let's say 0.0000001. So you got the log of like a billion. It's gonna send your pH skyrocketing really high, which makes sense because that's what we expect when we add base. But Henderson-Hasselbalch fails because the excess small approximation doesn't work out anymore.
Okay. And that kind of relates to like the homework when we were talking about like or I guess homework 5 asks at the beginning, like some conceptual stuff about like when the different assumptions fail, like that water isn't contributing much base in a titration or in a buffer. Like how do you, like what justifies that assumption? And like, I don't know, I guess, could you just go over like all the X's small?
Sure. So we've got a couple different approximations that we're using. The water not contributing is always based off of the autoionization of water. The fact that H2O plus H2O goes to OH minus plus H3O plus. And the equilibrium constant for that is 1 times 10 to the minus 14. Right? So water really doesn't contribute much. If I calculated the concentration of this OH minus, it's probably bigger than 1 times 10 to the minus 14 or 1 times 10 to the minus 7. So water's not going to contribute there.
Okay, but if it were to be smaller than 1 times 10 to the negative 7, then you would realize there's an issue.
Yeah, so if we were dealing with the situation where we have a dilute acid, a very dilute acid, then water might contribute in a significant way. So we have to watch out for that. We typically avoid that.
Okay, so that probably wouldn't be on the midterm, like a problem with the water contribute.
Well, we did one in class.
Where the water, like for this example?
No, we did it for a strong acid.
Could you do another example of that?
Yeah, let's check. Let's finish up with buffer calculations and considerations. So that's the first approximation.
Okay.
The second approximation, the way they word it is strange for buffers or weak acids, but it is the disassociation of a weak acid is negligible compared to its original concentration. That's a fancy way to say X is small.
And that makes sense because it's got a low Ka, and so it like,
Exactly.
Associate.
Exactly.
And that doesn't, like it was saying, does it work for a strong acid or a strong base? And that doesn't work in that case.
Yes.
Because for a strong acid and a strong base, we've got 100% disassociation.
Yeah.
X is large.
Yeah. Okay.
Question.
How do we calculate the pH for the DI water after 1 milliliter of NaOH?
This is a great place to look at, see if water contributes or not. So let's look at how we calculate the pH of just a deionized water situation. I'm going to erase the board unless there are any protests. Okay. So
I just have a quick question. Would this calculation that we're about to do be the same for tap water?
yes.
Okay.
Right, so the ion presence in tap water shouldn't affect the pH. The reason it does affect the pH is because of a secondary effect with carbon dioxide dissolving into water.
Okay.
Carbon dioxide dissolves better into deionized water than it does tap water.
Okay.
So tap water's pH is almost exactly 7, while deionized water's pH is almost like 5 or 4.
Okay.
It's really fascinating to me. Trying to think of how I can make an exam question about that now. So let's focus on water contribution, right? So how much base did you put into water and how much water was it?
Is that supposed to be on here?
I
Yes.
think it was like 50 milliliters of water. All the beakers were the same.
So I'm pretty sure everything used 50 milliliter portions to try and keep it consistent. So we're always using the same volume. And you should have been adding just 1 milliliter of the 0.1 molar, right? Right, so we wanted to see, we did this to our original buffer, we did it to our dilute buffer, and we did it to water to see how. So if we do it to our dilute buffer, water, we essentially can think about this as OH minus being added. We can think about this in terms of the H2O equilibrium. This is a common ion effect. So we've got H2O plus H2O goes to H3O plus OH minus. I have to be careful with my states of matter on this one since water is a liquid. Apologies to anybody who's been watching the streams and been like, your states of matter aren't there. No, they haven't been. We're going to set this up as an equilibrium table. I'm not going to care about the liquid. I'm just going to care about the H3O plus and the OH minus. This is going to be a 0. Again, as soon as I write that 0, I'm assuming water is not contributing. Well, I'm figuring out how much water is going to contribute. The OH minus actually has some concentration. I'm going to have 1 times 0.1 divided by 51. Why did I do that?
It's total volume 51.
Total volume is 51. Number of moles is milliliters times molarity divided by milliliters gives me my new molarity. Right? So I got moles over milliliters. That's going to give me my volume. Molarity. Words. It's Monday. Someone help me out with that calculation.
Should be 1.96 times 10 to the minus 3.
0.00196. Essentially, what we're calculating right now is the contribution of water. Right? At this point, we can probably say, hey, water doesn't contribute. And this is going to be my concentration. Take the negative log of that, and I'm done. But for the sake of argument, because we do have a midterm this week, let's say, hey, does water contribute? Let's calculate how much, let's calculate whether water's contribution is significant or not. So I'm doing the equilibrium of water. I'm going to have plus x. I'm going to say this is x. I'm going to say this is 0.00196 plus x. Notice I am not making the x a small approximation here. I probably should, though, because I don't feel like getting on Wolfram and solving a quadratic. So let's use x as small, and then we'll see if it's good. So right now, what I just did in this x is small approximation, I just said water doesn't contribute, right? Because I'm looking at the equilibrium of water, I'm saying it doesn't matter. Let's find out if that's a good approximation. So I'm going to have Kw equals x times 0.00196. This is going to be 1 times 10 to the minus 14 divided by 1.96 times 10 to the minus 3 is equal to x. Someone with a calculator help me out.
About 5.1 times 10 to the minus 12.
So I'm going to compare it to where I made the x is small approximation. 1.96 times 10 to the minus 3. Is water significant?
No.
Definitely not. If I compared these two numbers, the fun way I like to compare these two numbers is I do 0.00196 compared to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 5, 1. That second number is not going to matter. See ya later.
So then just to clarify, once we do like the negative log of that 0.00196, then we do the 14 minus that, right?
If you're trying to get the pH, yes.
Okay, cool.
Yep, that's it.
And it would make sense if it was something like 11.3-ish.
Would it? Is a base in water basic? Yeah. So it does make sense.
Okay.
Yeah, it totally makes sense. A base in water is basic.
Wait, what did you get? Your 11?
I got
So,
11.2.
Water's not significant, right? So the situations where water might become significant is if this gets down to 10 to the minus 7. Because notice the important ratio here is 10 to the minus 14 compared to the concentration.
And that's like a pretty big difference.
Yeah.
Okay.
So at that point, we're okay. See ya. So places where this gets important. There's 3 places where this gets important. When we are looking at the leveling effect, part of the leveling effect is when the x is small approximation fails. When you're looking at all you've got is acid, when you're looking at your base is really dilute or really weak, no, dilute, very low concentration. When your base is very, very low concentration, when your acid is very, very low concentration, so at one end of the pH scale, at the other end of the pH scale, And then in the very middle, when both acid and base are low concentration, close to 7. Those are the 3 spots where water starts to play an important role.
Thank you.
Let me see it.
Okay. I think that I remember seeing that. Oops, I think I remember doing that example. I just need to go.
Yeah, we did it maybe 2 weeks ago, right when we were first looking at acids. We looked at it.
Because we were talking about the pH, and the pH didn't make sense, right? Because
Right. Yeah. So if you do a dilute acid into water, and you do the calculation, you find that it's basic because you are neglecting the contribution of water. So once you take into account the contribution of water to that dilute acid, you get a pH of like 6.97 instead of 7.03. Yeah, that was an example from like 2 weeks
yes,
ago.
I remember those numbers now.
Question before you go?
Yeah, so was our original buffer supposed to increase in pH when we added 5 mils of NaOH?
It should increase,
dramatically?
but not dramatically. Right, and why not dramatically? There's a couple key
Because
words.
there's more acid.
Yes. The
There's
other
more
thing to think about, right, yeah. You remain within the buffer capacity
Oh,
because
yeah.
there are more moles of weak acid than moles of strong base you are adding.
Thank you.
Don't want to see ya. I'm gonna go ahead and stop the stream, I think, with this number of people. Okay. Goodbye.